Good day everyone. Today I'll be sharing key insights from our anaerobic digestion experiment where we explore the impacts of pH, temperature and feeding patterns on biogas production. Using multiple anaerobic digestion bags, we collected data to assess performance across different setups. At the end, I'll discuss how these findings could support scaling up to larger 800-litre bags with the goal of benefiting informal settlements in South Africa through sustainable energy solutions. For this experiment, we used 10-litre anaerobic digestion bags and 10-litre gas capturing devices. Bags were fed 3 times a week, Monday, Wednesday and Friday. On feeding days, we removed 800 milliliters of liquid, measured the pH, and added 800 milliliters of fresh feed. This feed consisted of diluted solids, kitchen scraps like potato, cabbage, tomato, and banana peels that facilitate microbial activity. We measured gas volume and temperature daily for each bag. Before discussing our findings, here's a brief overview of anaerobic digestion. This process involves microorganisms breaking down organic matter in the absence of oxygen to produce biogas, composed mainly of methane and carbon dioxide, through 4 stages. Hydrolysis breaks down complex molecules into simple sugars and amino acids. Acidogenesis converts these molecules into volatile fatty acids or VFAs. Acetogenesis breaks VFAs into simpler compounds like acetic acid, essential for methanogenesis. Methanogenesis. Methanogens produce methane under specific conditions such as neutral pH and optimal temperatures. Our first key finding was on feeding cycles and gas production. We observed the lowest gas volume on feeding days, with a peak the day after. This delay occurs because, initially, microorganisms are focused on hydrolysis and acidogenesis. Closer to the end of the day, VFAs and simple molecules become available, allowing methanogens to increase methane production. This lag in peak gas output is a natural part of the digestion cycle and indicates balanced microbial activity. Our analysis showed that Group 1 consistently produced methane at 50% to 67%, even when the temperature dropped by 5 degrees Celsius. While lower temperatures decreased overall gas output, methane levels remained stable, indicating the resilience of methanogens in producing quality biogas despite fluctuations. Temperature had a noticeable impact. Group 1's gas output was highest at 31 degrees Celsius, within the mesophilic range, 30 to 40 degrees Celsius. When the temperature was reduced to 26 degrees Celsius, daily gas production fell from an average of 12 liters to 9 liters. This highlights methanogens' sensitivity to temperature, which directly influences gas volume. pH proved critical. Group 1 maintained stable pH between 6.9 to 7.1, ideal for methanogens, which supported consistent methane production. Neutral pH balanced acidogenic and methanogenic phases, preventing harmful acid buildup. For Group 3, starting pH was 5, delaying gas production until adjusted to 7 by August 20th, at which point the system began producing biogas. Our feed, diluted to 4% solids, ensured gradual breakdown and steady nutrient supply. Group 1's stable feed solid percentage allowed us to isolate temperature's effects. Other groups used 3% solids and maintained average methane levels of 50 to 60%, showing that balanced composition supports sustained microbial health and methane production. Groups 3, 5 and 7 initially had low pHs, delaying methanogenesis. After adjusting to a pH of 7, biogas production increased. Group 6's replacement bag, set to 31 degrees Celsius and a pH of 7 from the start, quickly reached steady-state production, underscoring the importance of initial stability for microbial activity and consistent gas output. In conclusion, our results highlight the importance of feeding cycles, temperature, and pH in anaerobic digestion. Methane production peaks a day after feeding, aligning microbial activity with nutrient availability. If upscaled to 800-liter bags, as could be beneficial in informal settlements, these insights are essential. Larger systems may stabilize temperature naturally, but careful pH and temperature management remain crucial. Delayed peak production suggests feeding could align with peak energy needs. These findings provide a foundation for designing larger community-scale biogas systems to offer a sustainable energy source. Thank you for joining us in exploring our experiment. I hope this presentation has provided meaningful insights into anaerobic digestion and its potential for sustainable energy production. Thank you.